So yeah, I've done this question once before. So in this attempt, if hopefully I won't get the same question again, then I will continue. If I get the same question, then I'll reset the attempt and do it again. I looked up the title of the previous attempt. Let me look at the screen so that I can be sure that I can recognize it. Kinetic theory of gas. I kind of have a sense of what that would look like, but let me just be sure. Yeah, so it's going to be those descriptions. Yeah, if I get that, then I will stop the attempt, reset it, redo it. If I get something different, of which there's a pretty good chance, then I'll continue. Hopefully, I remember everything. And here's my pen. All right. All right. I don't think this is kinetic theory of gas. At least, yeah. So, so it says consider a gas of helium at a given pressure in some container at some temperature. Where needed, use this. How many particles? Yeah. So let me just write down the numbers on the side, and then I'll use O from alpha as my calculator. I am using ideal gas law. PV is equal to NKBT. This is the version we are using, not the one with the gas constant, but one with the Boltzmann constant. So solving for N is gonna be PV divided by KBT, and I'm just putting in the numbers that they gave us. 122 kilopascal times the volume, 0.01 meter cubed, divided by Boltzmann constant. I'll have O from alpha look that up, times the temperature, 322 Kelvin. And this will give you number of molecules, number of particles, not moles. Again, we are not doing that because I hate arbitrary constants. 120 kilopascal times 0.01 meter cubed divided by Boltzmann constant. Boltzmann constant is almost an arbitrary constant. So I could tolerate that, but I won't deal with Avogadro's number. Okay, 2.74 times 10 to the 23. 2.74 times 10 to the 23. That's the answer. Good. Suppose that the pressure of this gas changes. Describe the space below. Which of the following quantities necessarily change? Explain your answer. And the quantity that do not necessarily change, well, additional information is needed. Quantities, temperature. So one does not temperature does not necessarily change. It depends on how volume changes or doesn't change. Mass of gas does not change, as it depends only on the type and of the I'll just say number of gas. Internal energy, if pressure changes, internal energy, I'll say does not change provided that the temperature doesn't change. If temperature changes alongside the pressure, then yes, internal energy changes with the temperature. It's really the temperature that indicates the internal energy, not the pressure. Force on container wall. Container wall does change as pressure is defined as a force per area. Force per area. So pressure decreased or changed. So force changes proportionally to the pressure. Yeah, I think that choice number 4 is really what I was getting at. This is the only quantity directly related to pressure. Ideal gas law relates pressure to other things, but it involves other variables as well. Volume is the other one, so or temperature if we are looking at things other than temperature. So okay, suppose that the temperature of this gas changes. What quantity is necessary? Yeah. So internal energy, as we said above, internal energy does change according to the equipartition theorem. Internal energy is proportional to temperature in absolute scale. In non-absolute scale. Kelvin scale is one. There are other scales out there. Pressure does not necessarily change. It depends on how volume changes or doesn't change. Again, going back to ideal gas law, it's got 3 variables. So you tell me one of them changes, doesn't tell me anything about the second one unless I know, how a third variable changes. Volume does not necessarily change. It depends on how pressure changes or doesn't change. Pressure times volume does change proportional to temperature. But individual part, you have to know what the other part is doing to know what any one of those parts are changing. Sorry, extended this out too far. Oh, I could have done this earlier. All right, number of gas particles. Number of gas particles does not change unless the gas was allowed to leak out or in. I mean, we usually treat n here as a constant, not variable. Temperature alone won't change the number of particles. Mass is conserved, I'll say. Mass is conserved. Or material is conserved. Suppose that one of the following quantities changes as described, stated in the space below. If the internal energy of gas necessarily changes, or what other quantity needs to change to keep the internal energy the same. All right. So many parts, so much writing. I'm glad I'm typing it, not handwriting it. So pressure increases. Then 1, internal energy does not necessarily change. 2, in order to keep the internal energy the same, volume should decrease in inverse proportion to pressure, so that PV, pressure times volume, is a constant. Yeah, for NKBT. If mass of gas changes, you know what? Internal energy doesn't change. Equipartition theorem. Yeah, then internal energy does not change at all. Because according to equipartition theorem, each provided that the temperature remains constant, because according to the equipartition theorem, each quadratic degree of freedom stores energy 1 half kb times t, and this is independent of the type or mass of the particle. Caveat regarding additional degrees of freedom that may come in with diatomic versus monatomic gases, which isn't involved here. But if we was replacing helium with oxygen, then you might have to say, oh, at the same temperature, now there's more degrees of freedom, so more internal energy. I'll say 2, not applicable. 3, temperature decreases. That means the internal energy of the gas necessarily changes. Although if we were looking hard for corner cases, we could try changing n number of particles or the degrees of freedom, so that the total internal energy n times d divided by 2 times kBt remains the same. T is equal to 3 for monatomic, 5 for diatomic at room temperature. Yeah, but I'm just making up absurd cases. Internal energy changes if temperature changes. That's the most reasonable conclusion. There should have been 1. Okay, last one, 4th. The type of gas changes. Oh, yeah. So yeah, this is the scenario described above. So assuming that the temperature stays the same, then the internal energy of the gas does change, because we are changing the degree of freedom in E int is equal to n times d over 2 times kb times t. To keep the internal energy the same, we would have to change the temperature, more likely, or the number of particles. And yeah, those are the 4 cases. Lots of writing, but I think this is a fairly easy question. I mean, I had the one where I had to plug in number, and that was it. The rest are, and I think I did structure part 1 and 2 this way. So part 1 is more of a thermal physics intro, and part 2 will involve heat engine stuff. So when I submit, this should be graded as correct. The rest needs manual grading, so it'll say it's wrong or it's got 0 provisional point. Save work and continue. Yep, got credit for part A. And the rest of the parts, oh, I don't have access to answer key. It's fine. These answers are correct. Or, to the extent that there might be differences of opinion, yeah, it's an open-ended question. As long as what you can clearly reason it out, have good physical grounding for what you're writing, that's fine. Common assumptions are also fine, even if you don't explicitly state as I've done somewhere here. So, yeah, so that's it for this question. Good.